Hello, everyone. Good afternoon. Okay, welcome back to CS596. So today we will start a new chapter for convolutional neural network. So I think you may have heard the term before you're taking this course because it's one of the most popular buzzword when people reports machine learning or deep learning techniques. Okay, so indeed, convolutional neural network, or sometimes we use a shorter term, ConvNet or CNN, to indicate such a special neural network based model or special type of neural network. So it's particularly useful for image related tasks when the input is image data that consists of pixels, large volumes of pixels. And because the data is so big that we will find that it is really difficult to handle efficiently if we just use traditional model or traditional multi-layer deep neural network models. So we will look at this special type of neural network model, and basically we want to go through the fundamental convolutional operation first. Okay, then we will introduce terms like padding, strided, convolution over volume, and then pooling. Okay, so having these basic building blocks introduced, we will then start with some simple convolutional neural network as an example, and then introduce more complex model architecture. Okay, so the outline for this page, I don't think it's complete yet. Yeah, so for the applications, the ConvNet or CNN is actually very broadly applied to various types of tasks, not just object detection, but it's a lot of different types of applications. So object detection is just one of them. And the focus of this course is not focused on purely computer vision related tasks. So we won't spend too much time dive down into the details for object detection algorithms. Yeah, but we'll basically look at how ConvNets are used in those different types of applications. All right, so let's get started. All right, so the ConvNets, as I said, it's usually most commonly applied to computer vision tasks. Okay, like in self-driving car, face recognition, object detection, and so on. Okay, but it's also one of the useful building blocks for other tasks, even if it's not image input data, like in natural language processing. When the input is text, the CNN is also useful to as a automatic feature extractor or feature extraction components within those applications. Okay, so this plots is a typical presentation for the object detection application, like those positions, detected positions of objects and the labels together with the probabilities are how a ConvNet-based application can output to such detection tasks. Okay, so another application is we can use ConvNet as an encoder or automatic feature extractor to extract abstract features for input images. In this case, we can use ConvNet or use the internal representations of ConvNet to represent the styles or artistic styles of different images. And then after the style is learned from a subsets from one particular artistic style, artistic type, then we can apply that style to like arbitrary inputs. We can basically transfer the style learned from one type of picture to the other picture. Okay. All right. So in order to get started, we will first talk about the difficulty when we take image as input. Like if we use a small image, like 64 by 64 pixels image as an input example, then it's actually a pretty large vector if we take each pixel out and put them into a long vector, right? Lay them into one line or one column. So that'll be 4096 long vector, okay? So if that is the input, then if we are using a traditional or regular neural network, what would be the size for the first weight matrix, right? Without knowing about the internal units, about the hidden size, at least it will be something by 4096 columns, right? Because the input is a 4096 vector, so the weight matrix would be inevitably that large. Okay, so in a more extreme case, when the input is 3 million pixels, then it's obviously not feasible to use a weight matrix that has 3 million parameters, right? Although it's not uncommon that we see large models comes with millions or billions of parameters, but if we use a 3 million parameter for just one layer, then it's obviously not a cost-efficient operation. Okay, so and because it'll be like invisible for the computer to run, right? For the program to run, it will cost too much memory space, and not to mention the other issues like overfitting. We are using just too many parameters. So that is basically why we need a convolution operation. Okay, and to start with, we will look at a convolution operation at a 1D space first. Okay, so by 1D space, I mean the input is a 1D array or 1D vector. It's not an image, but it's just a one-dimensional array or vector. Okay, or you can call it a signal. So when a signal is like this, a string of number, and in order to conduct convolution operation, we will need a filter, or sometimes we call it a kernel. Okay, this kernel is usually a short fragment, short window or area of fixed length. Okay, in this case, this short filter is just 3 numbers, 3 real numbers, and it's just 3 cells, and each cell is the same value. It's 1/3. So what this filter, when this filter is applied to the signal S, mathematically we can write a formula like this. We can use the summation of a bunch of products to indicate the convolution operation of this filter on top of this signal. So this 1D convolution operator, if we visualize, it's actually pretty straightforward. What we actually do here is that we first align the signal and the filter at the left end, and we compute the summation of multiplications with all the overlapping elements. In this case, the filter overlap with the first 3 elements within the signal, which is 10, 50, and 60. right? So the result of 10 times 1/3 plus 50 times 1/3 plus 60 times 1/3 would be 40. And that 40 would be the first elements of the output. Okay, the output of the convolution is still a vector. So H1 will be the first element in the output. Then we will move the filter one grid or one step towards right. Okay, which means we slide the window towards right for one step. And in the second step, the filter is covering three new elements. Well, not necessarily brand new elements, but it's like a three new position that covering three elements. And we will do the same thing, summation of products to compute the second elements in the output signal, which will be still 40. Okay, and the third element, right? Fourth element, and then fifth element. Okay, the fifth element will be the last element within the output, because at this step, the filter is already hit the right boundary of the input signal. Okay, which means we have do a complete trip by sliding the filter window towards the left, from the left to the right, right? Okay, so we take all the outputs that is generated along this sliding process, right? We can take all the elements out, okay, which give us a new vector H, and it is just the output value of this convolutional operation. Remember, it's just the simplest case for a 1D operation, convolution operation. And if you look at the length of the outputs, it's actually determined by the simple arithmetic principle that we use the length of the signal, which is our inputs, minus the length of the filter plus 1. Okay, that'll be 7 minus 3 plus 1, which will be 5. Okay, and this principle is also obvious because if you are using a shorter filter, then you have more possible positions to place your filters, right? You have more steps to go within that sliding operation. If your filter is on the other side, if it's a very large filter, then you can only move for a very few steps, right? So the length of signal minus the length of filter actually makes sense here. Okay, so next we're gonna look at a more complex, which is a more advanced version of convolution operation. And this two-dimensional operation is the most commonly used case for convolution operations, and it's actually what we focus on in this course. Okay, because we are dealing with inputs image. We're dealing with image as input data. Okay, we have our input image represented by this 6 by 6 matrix of numbers. Okay, and you can think of it as the grayscale. So those numbers represent the grayscale value of a basically an image that is black or white. Okay, so it's not a colored image. For colored image, we're gonna see that it will coming with more channels. Okay, so in this case, there's just one channel. Okay, which just means it's just one slice of a 2D matrix. Let's see how a convolution operation in 2D space is carried out. Okay, we will still need a filter. Okay, but this time the filter is also a two-dimensional one. So it's a 3 by 3 small matrix, or small window as a filter, and each cell, each one of the 9 cells also has a value, has a number in it, which is 1/9. Okay, so I put the 1/9 outside the box because I don't want to write 1/9 to each cell, but this 1/9 here means that this 1/9 times will time with each ones in the cell, which means the actual values for the cell would be 1/9 each. All right, so that's what I mean here. So the outputs of this 6x6 image convoluted with a 3x3 filter would be a 4x4 output. Okay, and let's see how this 4x4 output is generated. Okay, we will, so in order to compute the first elements in the output unit. Yeah, so I see a question, and that is actually a very advanced question, like how do we decide if the filter is good? Yeah, so for that question, I think it includes at least two small questions. Like first, how do we decide the size of the filter, right? Whether it should be 2x2 or 3x3, right? And the second question is like, what are the values? How are these values decided? Okay, so these questions are something we're gonna answer basically by the end of the chapter after we have learned convolutional neural networks. Okay, all right, but we will have some first have some peek about different filters may have different effects on the outputs first. Okay, all right, the first elements at the upper left bottom here. So this value is computed by the 3x3 region in the original inputs, which contains these 9 numbers, 600144399. And what we do is to compute the summation of products with the green region here with the filter. So it's actually this summation of product is a kind of a dot product, and the dot product is like the multiplication with each value in the input region with the filter, and we then sum up all the products. Okay, so you can think of that we take the filter and we put it on top of the left upper left corner in the inputs. So each element corresponds to 1/9 in the filter here. Theoretically, the filter can be different shapes. Yeah, but actually, the most common practice is that we will make it a square, like with fixed with the same height and width. Okay, so that's how we compute the first value. If we do the computation, it will be 4. Okay, that's how we get it. And you can imagine how we do the rest of all the inputs, or how all the output units, cells in the output matrix. The second one would be the dot product. Now we move the filter by 1 step, which is 1 pixel or 1 grid in this cell, in this on this input image, right? We moved 1 pixel to the right. Okay, it will be 4.9 after the computation. Okay. The third one is another 1 step towards right. Okay, until we hit the right edge or the right boundary of the image. Okay, it'll be 5.7. All right, so when the first row in the output is done, right, we now need to go to the second row, right? So the second row, the first element of the second row would be using this region, right? We will move downwards for 1 pixel, right? Use this region to compute the dot product with the filter. Okay, then until we have scanned through all possible regions within the 6x6 image images region. Okay, so as I said, different filters. The question has from Sargent has raised that different filters have different functions. So that is something we will now look into. So this effect of the filters, I think it kind of belongs to the realm of traditional computer vision tasks. It's like we use certain predefined filters to conduct certain specific tasks. Okay. All right. So the filter in the middle that has 1/9 in all the cells, it's called an averaging filter. So we already know the output is like this. The effects of the outputs, the effect of this averaging filter is that it takes a region among within the inputs and computes the average values, right? Aggregates the pixels in that region into some average value. So you can imagine that the outputs should create some blurring effect. Right? It's aggregating the information, the pixel informations. Okay. So, and of course, the image size also shrinks a little bit. Right. So it's like a blurring effect. Okay. So I see the question that must the filter try to maintain the same aspect ratio? So you mean aspect ratio is the ratio of height versus the width? As the
Yeah, I think he's talking about it as like, could the filter be a 3x2, for example, when you have a 6x6 array?
Mm-hmm. So that's not necessarily, I think the filter doesn't necessarily be fixed, doesn't have to be like 3x3. It can be like 3x2. But as a common practice in convolutional network, it's still like filters of same width and height are the most common choice. Yeah. I don't think there's any particular reason, and maybe it's just for well, one thing that I can think of right now is that maybe a filter that is a regular square, right? The parameters in that filter, it's basically treats all the pixels from all directions equally. Okay, it's like doesn't assume that the local information within that image is suitable for a 2x3. Okay, so it basically assumes that the information is it's kind of a uniformly distributed spatially. It's a uniformly distributed in the spatial, in this little local spatial area. Yeah, I'm not sure if I made that clear. Yeah, but it's a most common choice to have filters of the same width and height. Yeah. Okay, so after the averaging filter, we will look at this identity filter. Okay, so the filter is like there's only one non-zero elements in the middle, and the surrounding elements are ones, are zeros. Okay, so it's called identity. Basically, it's what it does is that it's only copy the elements that at the central region to the outputs. Okay, right? Because if you take the first, when you do the first computation, right? When you apply the dot product with a bunch of zeros, 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 ones, zeros, so the 4 would be the only thing left, right? So the central area, the central element would be the only thing left. So of course it crops the elements by removing all the elements, all the 1 pixels, 1 pixel rows and 1 pixel lines at the boundary, near the boundary. Okay, so but it doesn't change the image significantly. Okay, that's identity filter. And now the if we move the central elements 1 to the left, it's a more interesting shift left filter. Okay, it's basically copied the pixels that is like one pixel to the left of the central area. Okay, you will see like some pixels would be missing in the outputs image, in the outputs of the after we apply the filter. Okay, so these are just simplest filters. So now we're gonna look at this special vertical edge detection filter. And the filter looks like this. So it's like I have 3 columns, right? The first column are all ones. Second column are all zeros. Right column are all negative ones. Okay, so we assume that larger values in the grayscale pixel in the pixel values means brighter color. Okay, and smaller numbers means dark pixels on the right. Okay, so in the original inputs, it's also the left half is a bright region and the right half is a dark region. So this line, this boundary actually indicates an edge, right? Because it's a vertical line with contrast on 2 sides. The left side is brighter, the right side is darker. So let's see, what if we apply this filter to the inputs? It'll be like, right, all these filters applied, it will be 20 times 1 plus 0 plus 20 times minus 1, which actually would be 0, because all the elements, they eliminate each other. Okay, we got a 0. Then for the second step, we move the filter 1 pixel to the right. Then things are different. All right, we have these areas, they are all zeros. Okay, and the only thing that's left is the 20 on the left, which means we will have 20 plus 20 plus 20, which is 60. Okay, and then look at further, look to the left, to the right. Okay, the output is still 60, right? Until we reach the right edge, that'll be 0. Okay, all right, so we move the filter downwards by 1 pixel. We'll do the same thing by computing the areas, by computing the dot product, right? We'll have 60s. So if you look at the results, the original inputs looks like this, right? The left is brighter, right is darker, and the output would be a bright region in the middle. Okay, and this middle bright region actually indicates that there is a vertical edge. Okay, so this special type of filter is able to detect where the change of pixel values occurs, right? So it can detect the change of pixels near the edge area. Okay, if the pixels don't change significantly, right, or don't change at all, then the output will be 0. If there's a very big changes in the pixel values, the output of this filter is actually a pretty large value that indicates, that highlights the edges. Okay, so from the perspective of computer vision tasks, especially traditional computer vision methods, this edge detection is actually very useful in the early days, because in order to detect objects, we will need to first detect the contour, detect the edges, right? As a question, how would this work on diagonal edges, which is both horizontal? Yeah, that's a good point. So we can, later we'll see that if we like flip, like we turn the filter by 90 degrees, it will detect horizontal edges. Okay, and basically what we can do is to have a vertical edge filter plus a horizontal edge filter, and that will give us a filter that is basically able to do both detections. Okay, which is the kind of the diagonal filter detection. Yeah, Sachin, you have a question?
Yeah, Professor. I just want to confirm that when you say edge is always the center of that grid, or it can be anywhere.
No, the edge can be anywhere.
So let's say if on the example, the first column is 20 and the next columns all are 0, that edge can also be identified using these kind of filters.
Yeah, maybe in this particular example, because the 20 is near the is already near the edge. So if we say we have a larger picture and we have 20s over here, and we have zeros over here, right? So the filter should be able to detect that edge as well.
Okay.
Yeah.
Got it.
Yeah.
Thank you.
Yeah, the function of this filter is to detect any significant change in pixel values that occurs horizontally, like, because it's this 1 and the -1, it's basically contrast the difference. It basically magnify the difference of pixels towards the left and the right, right? So if the more difference the left pixel is from the right pixel, the output will be bigger values. Okay. All right, on the next slide, we're gonna see a horizontal edge detection. Okay, basically the same example. We just flip the direction of the filter in order to detect the horizontal edge. Okay, so far the filters that we have talked about, they are basically hand-coded filters with values. The values in the filters are fixed, right? We just tell the filter to have such values, like 1/9 or zeros or ones or -1s. Okay, like those filters, they are based on experiments, based on empirical experiments. Like people experiment a lot in the early days for computer vision tasks, so that the filters can generate desired outputs. Okay, so let's look at this well-known Sobel filter. It's a vertical filter, okay, but it has slightly different values at the central area. Basically, it highlights the difference at the central area more. Okay, so if we apply this filter on these black and white image, it will output something like this. Okay, basically, it's more or less like a vertical edge detection. So you can see the highlight here, right? The highlights of the vertical edges are highlighted. Okay, and if we apply a horizontal filter, right, the fingertips that maybe indicate some horizontal filters are highlighted, right? And if we apply a different char filter, well, you probably do the similar task, but with different effects in the output. But I didn't visually, maybe this effect is not that visible, okay? But the underlying difference, the output values would be different. Okay, and Laplacian filter is something that's a combination of the horizontal and edge and vertical edge detection. So it's like it can detect basically the edges that are along all directions. Okay, so you can see the edges, they are highlighted. Yeah, so the filters, I don't know. I haven't done these experiments manually a lot because the inputs in this case is grayscale, and grayscale is usually a number that is ranges from 0 to 25. But if we set a hard limit, like if it, let's say below 100, it belongs to black, and above 100 is white. I don't know, the edges may be more salient, yeah, because there's more sharp changes in the image. Yeah, that could be the case, I think.
Would there ever be a reason why you wouldn't want to use the fourth filter? I mean, I don't understand why you wouldn't want to look for both edges at the same time, both vertical and horizontal.
So that depends on the purpose of the application. Like in some cases, if I want to say extract all the boxes, okay, all the box areas or triangles in the image, then we will probably focus on only the edges in one direction. Yeah, it's totally depends on the application. Sometimes in some cases people are only interested about the vertical edge. In some cases it's just the horizontal edges. Yeah, and this Laplacian filter, I think it's just a very coarse application, a coarse algorithm for detecting edges. So the traditional computer vision tasks would use something like a cutting edge detector, which introduces more advanced, more sophisticated method rather than just applying a filter on top. Yeah, but that is not the focus of our chapter of computational of convolutional neural network here. We're gonna go a step further to see what we can do to replace these hand-coded filters into with some filters that have learnable parameters instead. Okay, so yeah, for the sharp filter, benefits over the vertical sober filter. They look the same. Well, I don't think they look the same, but the vertical edges are still highlighted, more highlighted in this Sobel filter. Yeah. Yeah. Anyway, these filters have different application cases. Yeah, but let's take a step forward, okay, and look at the next key step of the convolutional neural network. Okay. All right, so actually the step. Okay, I see another question. Robin's question. Why is the image not blurry? Okay. I don't know. You can call it blurry already because it's averages the area a little bit, right? But it's not a, well, first thing, it's not a averaging filter. So the blurring effects will mostly visible if we applied a averaging filter, okay? Because none of the filters we use in example are averaging filters. It's like contrasting the edges, but not averaging the pixels. Yeah. All right, so we need to take a step further. So because the filters, if we use predefined values for those filters, their usage is actually very limited. It's like we preset some values and then we apply those filters on top of whatever image we see, and then we will look at the output to see if the output is as expected. Okay, that is the traditional way of computer vision techniques. But nowadays, the convolutional neural network will use filters that have parameters in it. Okay, so the parameters are to be learned. Okay, they are not determined at the beginning. Okay, so by applying these filters that have parameters in it, we are able to generate some outputs. Okay, and then these outputs will be compared to some ground truth. Okay, so these ground truths can be primitive ground truths, like there's an edge in it or not, or it can be a very high level ground truth, like this is a hand that indicates 3 or 4, right? The label of the sign language. Okay, so it could the ground truth can be a high level label. So we will compare the outputs with the ground truth label, and it will create some cost or some loss, right? And then because we have parameters, those W1 to W9 in the filters, they are the parameters. We can compute the gradients of the loss with respect to those parameters, right? Those gradients can then used to update the parameters. So in the next round of computation, those parameters will have new values. It's just like how we set up the linear regression or logistic regression models, okay? But the difference is that now our filters, our parameters are in the filter, and how these parameters are computed with the input is like we use a sliding window, right, to compute a bunch of outputs, output value variables. Oops. So in the ConvNet model or convolutional neural network models, the parameters mostly exist in the filters that we use. Okay. So if this is no problem, we will proceed on to the next slide. All right. So now we will study the arithmetic rules of how to map the input to our outputs when we have some filters. Okay, so this is a general principles of doing these convolutional operations. Okay, when we have inputs, so in this example, when we have a 6 by 6 inputs and our filter is 3 by 3, then our outputs would be 4 by 4. Okay, because there are 4 possible positions if you are fitting a 3 by 3 filters into a 6 by 6 matrix. You can try sliding the window yourself. So in more generally speaking, when we have an n by n filter and an f by f, n by n inputs and an f by f filter, the output would be in this shape. It should be n minus f plus 1 by n minus f plus 1. Okay, so because it's also like you sliding the window around the n by n matrix. Okay, so you can see that there's obviously downsides of this. The inputs actually got shrinked, right? And the information near the edges is less used than the central regions. Okay, so the edge here, the corner pixel here is used only once, right? But the central regions indicated by this green area is actually used multiple times, right? So in order to address this issue, we will use the technique called padding. Okay, so the padding is to overcome the shrinking downside. Okay, so it's applied before the convolution operation, which means we will pad the inputs image. Okay, so now the inputs becomes from a 6 by 6 to a 8 by 8 by padding with one additional pixel along each direction. Okay, there are 4 directions. Okay, so the up, down, and left and right will be all padded with 1 pixel. That'll make the input from 6 to 6 to 8 by 8. Okay, let's call it n prime. Okay, and now after we apply the padding effect and the padding operation, and then apply the filter with the same size, what would happen is that the output becomes a 6 by 6 one. Okay, so using the principle of n prime minus f plus 1, which is 8 minus 3 plus 1, right, which would be 6 by 6. And the 6 by 6 is the same size the original input. Okay, which means we preserve the information. Okay, we preserve the original input size. Okay, so that is useful when we want the convolution to not change the size of the inputs. Okay, and
but wouldn't padding not always preserve the size? Like if your filter was, much bigger, right? So it's, if your filter was a 5 by 5, for example, instead of a 3 by 3, the padding wouldn't preserve much size. It wouldn't still be a 6 by 6 after filtering.
Yeah. So for different filter sizes, if you want to preserve the original size, you will need more paddings. You will need different.
Okay.
Yeah, you will need
Got it.
different.
So, yeah, it's not always going to be just one pad. Okay.
Yeah. So there could be different padding sizes. Like we can add 2 layers, right?
Oh, brilliant. Okay.
Yeah, that'll become like
too early.
Yeah, very thick frames to the inputs. Okay, so now we have a 10 by 10. So that means if we still apply this 3 by 3, then the outputs would actually be larger, right? The output would be larger. So these arithmetic principles can actually be summarized like this. Like if you apply a padding that is of size p, okay, then the outputs. So first of all, the n prime would be n plus 2 times p. So that is the n prime, right? So when your pad size is 1, then n prime would be n plus 2, right? So we just if the padding is 2, then n prime would be n plus 4, and so on, right? So we let's just insert the n prime into the equation, into the formula here. These would be the augmented inputs, n plus 2p, and then we apply the filter. That principle is the same. We minus the f plus 1, so this n plus 2p minus f plus 1 would be the output size. Okay. Let's see two common types of padding or convolution. Okay, so well, nowadays I don't think these terms are not that often used, but it's useful to look at the definition. So like a valid convolution, by that we mean that we don't use padding at all, like we don't add modifications to the inputs. So that means the inputs would always shrink, the output will be shrinked. And the second term, called same convolution, is that we will use padding so that the input size equals the output size. Okay, so we will let the n, which is the input size, and the n plus 2p minus f plus 1 as the output size. If we let these two variables to be equal values, then we can actually solve the padding size. Okay, so the padding will be determined by f minus 1 divided by 2. Okay, so how much padding we want in order to preserve the input size actually depends on the filter size, right? So in the example before, we use f equals 3, then the p would be 3 minus 1 divided by 2, which would be 1. Okay, so in order to preserve the size, we have to do a 1 padding. Okay, and if we do 2 padding, then that's too much. Okay, and if a filter is say 5, okay, then 5 minus 1 divided by 2 would be 2. So that means we need to actually do a 2 padding. Okay, so because if f is a even number, then this whole division is not a doable to generate integer numbers, right? So usually speaking, the filters that we use are usually odd numbers. All right. So I think I will introduce this last concept called strided convolution before we end the class today. So this strided convolution determines how big a step we take when we slide the filter on top of the inputs. Previously, all the examples we've shown, we will move the filter by 1 pixel at a step. Okay, but that step size can also change. Okay, like we can move the filter faster by 2 pixels in 1 step. So that will affect the output size actually. So now we use a 7x7 image as input, and we move the 3x3 filter, but we are using a stride of 2, which means like the first example would be the same, right? The first cell would be the same value, would be the dot product between the green region with the filter. Then the next region, we moved actually 2 pixels towards the right, and we didn't do the step in the middle here, right? Because we deliberately set the stride size to be true. Okay, so which means we scan the image faster, but of course we lose some granularity, we lose some like information in the middle. Okay, so we try that stride equals 2, we will have like a new value here, and then we try another step, and we immediately hit the boundary, the right boundary. Okay, so the outputs would be a 3x3 value. Okay, so now when we look at the second row, actually we need to move downwards also at a 2 pixel step. Okay, so this stride applies to both directions. And I think nowadays in PyTorch, in frameworks, we can decide the stride value for each direction. Actually, it can be different. Like if we want to go faster along the horizontal direction, right, and remain the same speed remain the old speed along the y direction, we can use stride equals 2 for x and stride equals 1 for y. That is also possible. Okay, but in this case, I'm just showing that we do stride at both directions, stride equal to at both directions. Okay. So yeah, that's how we compute the output. So now the outputs would be like in a more complex form. So yeah, Sachin, you have a question?
Yeah, Professor, what if the input is not 7 into 7 size, but 6 into 6 size in this example?
Yeah,
How?
so it could be like if it's 6 by 6. So let's imagine that if it's 6 by 6, that will be our first step. Then will be second step, right? Then the third step will not be a valid.
Yeah, that's my question. If 6 by 6 by 6 is not it's an invalid thing, so such inputs we don't do it. Or
in this case we don't do it. It will be the output will be a 2 by 2.
Okay.
Yeah.
Thank you.
So then it would just lose a lot of data.
Yeah.
Okay.
Yeah, and actually, luckily, because the inputs now we seldom deal with such a small images, right? So even a 6 by 6, 64 by 64 images looks very small to us. So unless you set the stride values to some like crazy large ones, actually this kind of information loss is still acceptable. Okay, so the general principle of applying stride is like you compute. So before stride, we have n plus 2p minus f, right, which is the original value decided by the padding and the filter size. And now because along that direction, we take the step of stride. So if s is 1, then the whole thing is not necessary. The whole flooring is not necessary. So if s is 2, then we need to decide how many steps we take. Okay. So s is the stride size. All right. So it's running to the floor, which means we will discard the remaining parts if it's not sufficient for another step. Yeah. I think Brandon has a good question. Like, I didn't do a very just like a comprehensive review of how stride is used. I think it's used in some intermediate steps that's processing the inputs with higher speed is okay, is acceptable when the most of the encoding step is done. Like we can have multiple convolutional layers. Maybe the earlier layers need to take the inputs more carefully, so they will have smaller steps, smaller stride, and maybe later steps can have larger steps. But I don't know. It depends on the model's structure. Okay, and I didn't do a lot of experiments with this stride settings. Yeah. Okay. All right. So yeah, here the 6 by 6 example just explain the rounding floors, the flooring rules. It's like we lose the last few positions. Okay. Right. So this will not be done. Okay. All right. So I think I will need to end the class earlier today. I have another seminar talk to give at 5:30. I need to prepare myself, so I will end the class earlier than usual. Okay, and we'll upload the video and release the quiz question. There will be a quiz question already on Canvas. Yeah. Thanks for coming, and have a nice weekend. We will continue our journey to more complex convolutional neural network next week.
Take care.
Take care. Thank you. Bye-bye.